Okay, let's go ahead and get started with video number 2 for hydroelectric power. We left off in the prior video talking about that when we're going to go ahead and analyze the penstock. So again, the penstock for a power plant is basically the fluid's path between an upper and lower water levels. So it'd be the water level prior and after the dam. And then the penstock also is the accumulation of all of the pipes that are used for the fluid flow path. Step 2 is we're going to take that information and basically look at different combinations of flow rate and elevation change and how that relates to the type of turbine that you would pick and what type of turbines there are for these type of power plants. So before we get started, let's take a look quick at this diagram. We have here our general penstock arrangement. Point A and point B before and after the dams. You can see point A is the higher end level and point B is lower end level. And then the penstock here, that the water flows through the penstock through a turbine to extract electricity. So in order to do this, we're going to go ahead and apply Bernoulli's equation between point A and point B, which gives us the following. So there's Bernoulli's equation. Between point A, we have our pressure, velocity, and elevation terms, and the same thing at point B. And then after it flows through, of course, we have some losses through the penstock, which I'll explain later. These terms are associated with the losses. And then we have a certain work term that's extracted from the turbine. So simplifying this equation should start with basically looking at the pressure, right? The pressure on each side is going to be atmospheric, and the velocity at the surface, A and B, is 0. So then these terms go away, right? So what I'm going to do is actually now take that equation and I am going to solve for the work term and then in terms of flow rate, right? So if I do that, I get the following. Okay, so now this is how the equation reduces. Again, we did was that we actually put it in terms of flow rate, so some of the terms changed. The velocity term from the prior slide, right? This velocity term got converted into flow rate. So with that said, let's go ahead and define a few things here. First off, these are what we would call minor losses, right, through the penstock. And G sub C is what we call the gravity constant. So in English units, it would be 32.17. And in SI units, believe it or not, it's 1. As far as the friction factors are concerned, for F sub n, we get the following correlation for laminar flow, or for Reynolds number less than 2300. And then if not, Fn is going to be an equation that's a little bit longer, which is the following. And this equation is valid for turbulent flow, or for Re greater than 2300. And the other friction factor for minor losses, again, will be equated to the following. And again, this D is for diameter. And then to actually get power, the power would basically be just density times the flow rate multiplied by the specific work, right? Which is where this is actually m dot. So that would be where we would end up getting the power from the hydroelectric power from the penstock. Let's go ahead and apply this to an example problem. So here's an example problem from the book. It says a proposed design for a hydroelectric project is based on a discharge of 0.25 meters cubed per second through the penstock and turbine, as shown in the figure. The minor losses are negligible. Determine the power in kilowatts that can be expected from the facility if the turbine efficiency is 85%. So again, here you can see the elevation is 915 meters, and then it decreases to 892 meters. And it gives us that the length of the penstock is 350 meters, the diameter of the pipes is 300 millimeters, and the relative roughness is 0.046 millimeters. If you're to go ahead and just take some time and look up the properties of water that we'll need, you can take a look at the kinematic viscosity. And we can also get the density. As well as you can write down the given flow rate. And this is no minor losses, so I'm going to assume the minor loss coefficients are 0, right? And again, that's assuming no minor losses. If you remember back earlier, we defined these terms as minor losses. So with that said, we can go through and just kind of like go through the calculations one step at a time. So let's go ahead and let's start with the Reynolds number. Go back and look up what the correlation for Reynolds number is, right? We get 4 times the flow rate divided by pi times the diameter times viscosity. You plug in your numbers there, which I'm not going to do. So you guys can do that on your own. But we should get about 931,000 as the Reynolds number. Now, that of course is definitely turbulent, right? So we're going to have to go ahead and use this long correlation to find out what the friction factor is. So if we compute this, we end up with a friction factor of 0.014. Okay, so we continue and figure out what the work extracted from this is. So I'll go ahead and write out the equation for work. So when we go through these calculations, again, minor losses aren't included. We get 112.9 meters squared per second squared. And if we use that to find out what the power is, taking in the right conversions, remember 1 kilojoule per kilogram is equal to 1,000 meters squared per second squared. That would have to be taken into account in this equation. Basically, we go ahead and we figure out that the total power, available power, is 28 kilowatts, and we know that this thing's operating at 85%. So this power plant itself would be producing about 24 kilowatts worth of energy. All right, well, thank you very much. This ends video 2 for hydroelectricity.